in the last lecture we proved this theorem which I told you about the precise number of elements in of order 2 in the ideal class group of an imaginary quadratic field, and we did that using the bijection with binary quadratic forms. Today we are going to look at some explicit calculations in some cubic fields. Okay. So, not all cubic fields, but cubic fields of a certain type. So, these are called pure cubic fields. Unlike quadratic fields which are necessarily obtained by adjoining square root of a number, cubic field a field of degree 3 need not be obtained that way. So, pure cubic fields are fields which are obtained by adjoining cube root of something. So, these are a pure cubic field, a pure cubic extension of Q is a field K such that K is Q cube root of some number. Okay. So, A is in Q cross, but not Q cross cubed. Okay. So, K over Q is degree 3, and necessarily this is not right. It's not a what do you say, a Galois extension. K over Q is not a Galois extension. So, of course, there are Galois extensions of Q also of degree 3, but those are not included in this. Okay. So, what we can do is we can assume by clearing out denominators, we can assume that A is actually an integer, and then we can write. So, I want to change notation here, we can write K as Q cube root of M, where M is in Z and M is of the form M1 times M2 squared, where M1 and M2 are co-prime square free positive integers, right, where M1 and M2 are so actually I can put that here as well. So, A is already positive integer, because if A is negative integer, cube root of A is minus of cube root of minus A, and they generate the same number field, right. So, M1 and M2 are square free positive integers. Okay. All right. So, what I can do then is I can put alpha 1 to be cube root of M1 M2 square, right, and I can put alpha 2 to be cube root of M1 squared M2, right. So, if you think about what the relation between alpha 1 and alpha 2 is, if I take square of alpha 1, then this is cube root of M1 squared M2 to the power 4, which is M2 times cube root of M1 squared M2, which is same as M2 times alpha 2. Right. So, alpha 1 and alpha 2, they generate the same number field, right. So, you get K is Q of alpha 1, or it is same as Q of alpha 2, right, because again if I take alpha 2 squared, I get M1 times alpha 1. Okay. So, there are these two nice elements in our field that generate the field on its own. So, we can look at what delta of 1 alpha 2 is, or delta squared of this. So, yeah, let us try to find this. So, this is equal to right, yeah, okay. So, okay, let me yeah, determinant of trace of 1. So, trace is from k to q now, trace of alpha 1, trace of alpha 2, trace of alpha 1, trace of alpha 1 squared, trace of alpha 1 times alpha 2, trace of alpha 2, trace of alpha 1 times alpha 2 and trace of alpha 2 squared. So, what is trace of 1? This is simply 3. What is the minimal polynomial of alpha 1? It is x cube minus m1 m2 squared, and the minimal polynomial for alpha 2 is x cube minus m1 squared m2. So, this trace is 0, this trace is 0. What is trace of alpha 1 squared? So, we know that alpha 1 squared is m2 times alpha 2. So, trace of alpha 1 squared is m2 times trace of alpha 2, which is again 0. So, this is 0, this is 0, this is alpha 2, this is 0, and then this thing is 0, right. And so, what is trace of alpha 1? Alpha 2. So, alpha 1, alpha 2, this is cube root of m1 m2 cubed and m2 square m1 squared m2. So, this is m1 m2, and so this is 3 m1 m2, 3 m1 m2, right. And so, if you calculate the determinant, this is minus 27 m1 m2, right. I hope you sort of understood this calculation. If not, you should do this calculation yourself, or computing the it is not quite the discriminant in all cases, but computing a discriminant like determinant. Sorry, this should be square. Okay. All right. So, so delta squared. So, here is the proposition that we proved. Delta squared of 1 alpha 1 alpha 2 is minus 27 m1 squared m2 squared. Okay. All right. So, this does not tell you much, it tells you that the discriminant of the field K could be minus 3, it could be it could be equal to this, of course, but it could be this divided by some square, and so you could divide by m1 square or m2 square or m1 m2 square or 3 square or 3 square times m1 square or 3 square times m2 square and so on. There are lots of possibilities, but actually most of these possibilities do not happen. So, here is a theorem that we proved today, right. Okay. So, let K be Q cube root of m1 squared, sorry, not m1, yeah, okay, let me same as Q cube root of m1 m2 squared, etc. Then with the notation as above, dk is minus 27 m1 squared m2 squared yeah, unless m1 is congruent to plus or minus m2 mod 9. So, if m1 is congruent to plus or minus m2 mod 9, then 1 by 3 1 plus m1 alpha 1 plus m2 alpha 2, this belongs to OK, and the discriminant in that case is minus 3 m1 squared m2 squared. Okay. So, that is what it is. So, discriminant is almost, unless m1 is plus or minus m2 mod 9, the discriminant is this minus 27 m1 squared m2 square, and in that case 1 alpha and alpha 1 and alpha 2 is a basis for OK. If not, then you have to include this one more element, and then you get then you can generate OK. All right. So, proof and so even for finding the ring of integers of a quadratic field, we had to do some work, right. It was not a pure thought kind of proof. We had to find out what the discriminant could be. So, we took 1 and square root of m, and then we said let us find delta squared of 1 comma square root of m. We got 4 times m, and so the discriminant could be either m or 4 times m, and so we took cases, and there is nothing different about this. It is a bit more complicated, but the basic idea is very similar. So, and of course, because we are taking cube roots, 3 will have a special place in this, and that is what we will see. So, let p not equal to 3 be a prime factor of m1, right. M1 will have a prime factor. You can't take m1 to be, I mean m1 is not 1, because otherwise you are just adjoining, m1 could be 1, but both m1 and m2 can't be 1, because cube root of 1 is 1, and so you won't get a cubic field. In any case, so let us say there is a prime factor p dividing m1, then here is a claim. If you take the ideal generated by p and alpha 1 and take its cube, this is same as ideal generated by p, right. So, p ramifies in, so this means hence p ramifies in k. Once we prove this claim, we will get that p ramifies in k. So, how do we show this? So, there are two ways of showing this. Let me give you the explicit way as a kind of exercise, and then let me show you. Okay, so two ways of proving the claim. Two ways of proving the claim, right. So, one is maybe you use Dirichlet's, so maybe exercise use Dirichlet's theorem. Right. So, you will have to make sure that hypothesis for Dirichlet's theorem are satisfied before you do this, but we can do it explicitly, or we can do it explicitly. So, you take p and alpha 1 cube, this is same as the ideal generated by p cube, and p square alpha 1 and p times alpha 1 squared and alpha 1 cubed, right. So, this is same as p cubed, p square alpha 1, p alpha 1 squared, and then m1 m2 squared, right. Okay. So, this is same as p cubed times p square alpha 1, and then p, what is alpha 1 square? We computed this a little while earlier, and this turns out to be m1 times alpha 2, right, and then m1 m2 squared. Now, you notice that GCD of p cubed and m1 m2 square, this is equal to p, right. So, the ideal generated by these two is precisely p. Okay. And then p also contains the ideal that and p square divides p m1 alpha 2, right. So p square divides okay, let me not write alpha 2 here, but it does not really matter because p divides m1, right. So, p square will divide p times m1, and so you see that you can always take a linear combination of first and the last element, so that you can get p, and then all the multiples of p will also be here. So, this hence p is contained in p alpha 1 cubed, right. On the other hand, we know that that this cubed is contained in p alpha 1, right, which right. Okay, I think that is not really relevant. Okay, fine. Okay, so how do I finish from this point onwards? Yes, so I need to show that if I have any element in this this cubed, then it is divisible by p, but we have already shown that each of this element is divisible by p. So, so these two together imply that p alpha 1 cubed is contained in p, right. So, hence we are done with the claim. So, that is an explicit way of proving the claim, right, or you could use Dirichlet's theorem as long as you have all the hypotheses satisfying. So, p ramifies in so hence p dividing m1 ramifies in k. Similarly, p dividing m2 satisfies that p alpha 2 cubed is p, and hence it ramifies in k, right. So, this means that p square divides so this means that p divides dk, and we know that delta squared 1 alpha 2, this is equal to some a square times dk for some a in z, right. Now, p square divides delta square and p divides dk. So, this implies that p square divides. So, you know, this implies that p does not divide, let me write it this way, p does not divide a. Okay. So, so this is for any p dividing m1 or m2, right. And so, this means that a is either 1 or or 3, right, as I said, as the theorem says, A is either 1 or 3. So, we have to find out which one it is, right, and then if this is the case, then dk is equal to minus 27 m1 square m2 square. If this is the case, then dk is minus 3 m1 square m2 square. So, we have to find out which of these two cases we are in, depending on a congruence between m1 and m2 modulo 9, right. That is what the theorem asks, tells us. And so, we have ignored the prime 3 up to this point. So, we have to consider the prime 3, right. So, again we are going to take two cases. So, let us say 3 divides m1 for the sake of concreteness. Then we know that the ideal generated by 3 is equal is cube of some ideal, right, ramifies in K. And why is that? Well, because what is this ideal? This will be sort of alpha 1 times 3 cubed, right. Okay. Furthermore, you can see that P3 is the exact power of P3 dividing alpha 1, and P3 square is the exact power of P3 dividing alpha 2, right. Okay. So, now we are going to analyze a general element in K. So, let C0 plus C1 alpha 1 plus C2 alpha 2 be in K, be in OK, and C0, C1 and C2 be in Q. The only possible denominators of C0, C1 and C2 are powers of 3. The only possible denominators of Ci's are powers of 3, right, because other primes we have already ruled out. When we did this, right, the possible discriminant. Okay. Right. So, we look at the exact power of So, you have alpha, which is C0 plus C1 alpha 1 plus C2 alpha 2. So, the exact power of P that divides all of, so this is this times 1, right, and so the exact power of P dividing this is P0 to the power P3 to the power 0, and this is P3 to the power 1, and this is P3 to the power 2. And so, if you want P3, so if you want alpha to be an algebraic integer, then all of these things better be integers, because if they have powers of 3 in the denominator, then so let me write it this way. So, if Ci is equal to d, maybe d is a bad integer, let me write ei by 3 for some I, and ei in Z 3 does not divide ei, then okay, maybe I will do a concrete thing. Yeah, let me do a concrete sort of example. Let us say this is C0, E0, C0, E0, right. Okay. Then alpha is 1 by 3 E0 plus 3 C1 alpha 1 plus 3 C2 alpha 2, right. And so, this should be divisible by P3 cubed, but the only way this will be divisible by P3 cubed is if E0 is divisible by P3 cubed, right, in which case E0 will be divisible by 3, and we have assumed that that does not happen. So, that is a contradiction, right. So, hence alpha is in OK if and only if Ci's are in Z, right. So, so if 3 divides M1 and similarly 3 divides M2, then of course we have that 1 alpha 2 is a basis of OK, right. So, now we have to look at the condition. So, the only case left is 3 does not divide M1 M2, right. That is the last case that is left. Right. So, in this case what happens is delta squared 1 alpha 2, this is equal to minus 27 M1 squared M2 squared, but this is also equal to A squared dk, right. So, hence 3 divides dk, that is necessarily true, right. 3 has to divide dk, which means that 3 is ramified in k. So, hence we could have done that before as well. 3 ramifies in k. So, there are again two possibilities. So, there are two possibilities. And what are the two possibilities? The ideal generated by 3 is P3 prime P3 double prime squared, or it is the ideal generated by this is P3 cubed, right. So, we have to take into account these two possibilities, right, and see what happens. So, this takes a little bit of work. Maybe we will finish this next time. So, this time we started studying pure cubic fields. So, field extensions of Q that are obtained by adjoining cube root of a rational number, and we can assume that this rational number is an integer of a specific form, namely M1 times M2 square, where M1 and M2 are square free positive integers, and then we want to find a basis of the ring of integers, and there are two cases that we have to take, right. So, we will finish the proof of this theorem next time. Thank you.